In number 11, they want us to decide which substance would have the lowest boiling point. And so they're showing the way the particles are being held together. And you remember that there's this general trend that actual bonds, such as ionic bonds or covalent bonds, have much stronger bond strengths than actual intermolecular forces. These tend to be significantly weaker, and so if we're talking about breaking these, then that's going to lead to very low boiling points, as in it evaporates easily. So we're probably going to want to get rid of A, because ionic bonds are some of the strongest bonds, and if you break those, you actually aren't boiling anyway. If you break an ionic bond, you're actually doing a reaction. And same goes with metallic bonds. Those are actual bonds. So if you're trying to evaporate something, these are the only two that are actually intermolecular forces. And you remember the order of those is hydrogen bonds are significantly stronger than London dispersion forces. So B will be the answer. Those are the weakest intermolecular forces and will lead to the lowest boiling point. In number 12, we'd like to know which of the following species, remember species means things, does not have a tetrahedral structure. And so when you look through these, you notice they all have 4 substituents, and so you might think, well, they all have a tetrahedral structure, but of course there's no way to know that. Some of them might have lone pairs, and so we probably should draw out their Lewis structure. Now, you remember that in order to draw out the Lewis structure, you should always add up the valence electrons, then spread the electrons around the outside, then the inside, and see what you have left. Now hopefully you remember the structure of CH4. CH4, carbon always has 4 bonds, and since it has 4 hydrogens on it, there's no way it could have a lone pair. So since it has 1, 2, 3, 4 substituents, it is definitely tetrahedral. So we can rule it out right away. If we did NH4, we would put our hydrogens around it, and we would add up the valence electrons. Nitrogen brings 5, each of the hydrogens brings 4, that's 9, but you remember that we don't have 9 because it's positive, we have 1 less electron, so we have 8 valence electrons, and you notice that we already have used all 8 valence electrons. And we have none left over to go in the central atom, so there's no lone pair, and it turns out that NH4 is also going to be tetrahedral. So we can rule it out as well. And then we got to do the same with the last 2, and I'm going to draw their Lewis structure. Alright, so let's look at SF4. If we're counting the valence electrons, you notice I've already got things spread out here. If we're counting the valence electrons, sulfur is going to bring in 1, 2, 3, 4, 5, 6. Each fluorine is going to bring 1, 2, 3, 4, 5, 6, 7. 7 times 4 is 28. 28 plus the 6 is going to be 34. So we have 34 valence electrons to work with. It's an even number, it seems reasonable. We spread them around the outside first. And we've used 8 on each one. 8 times 4 is 32. We have 2 left over, so we do have a lone pair here. And you'll notice that we have 1, 2, 3, 4, 5 electron groups around the sulfur atom, and so it's definitely not going to be tetrahedral because they have to be 4. So I think C is going to be the correct answer, and I'll let you check out if G turns out to be on your own. In number 13, they're talking about benzene, and I think it's unlikely that on the actual AP test you'd have to remember benzene's structure, but you remember that its structure looks like this. And what they're talking about, the alternating single and double bonds, are like that. And you remember that at each corner here are carbon atoms, and you could actually draw in the hydrogens if you wanted to, remembering that carbon has 4 bonds. If we're looking at this carbon right here, it's already used 1 bond and then 2 bonds in the double bond, so that's 3. So it's probably going to have 1 hydrogen coming off of that carbon. And so you could draw in all the hydrogens if you wanted as well, because they'd each have 1 H coming off of them. Now let's look at their question here. They say that if the length of the single carbon-carbon bond is 154 picometers, so they're talking about this one being 154 picometers, and the double bond being 133, what length would you expect for the carbon-carbon bonds in benzene? And so this is another resonance structure question. What they're saying is that there's not really a double and a single and a double and a single. The double bonds are actually sort of partially everywhere. So instead of a bond order of 2 and a bond order of 1, each one is actually about 1.5. So we'd expect the bond lengths between these things, since double bonds are shorter than single bonds, we'd expect the true bond length of all of them to be the same, and it would be somewhere in between those two. So let's see if we can rule some things out. Well, we definitely can rule out D. It's not going to be 154 because that was a pure single bond. It's not going to be 133 either. And since we know it's going to be an average of the two, it can't be below 133. It's got to be between this one and this one. So I think C is going to turn out to be the correct answer. All right, 14. Which of the following could be the Lewis structure for sulfur trioxide? So in order to get this right, we should probably make sure we know what sulfur trioxide is. It's SO3. And maybe the easiest way is to just draw the Lewis structure ourselves. So we know that sulfur would go in the middle. We know that there would be a total of 6 valence electrons for each oxygen. That's 18, plus the sulfur is another 6. So actually 6 times 4 is 24. So we have 24 valence electrons to work with. We go around the outside like this. And then we've used 8 around each one. 8 times 3 is 24. We're done. So you might think, well, this one looks an awful lot like our structure here, so it might be a possibility. But sulfur does not have an octet, so I think that one's not going to be the answer because we got to share our electrons. So what we're going to do is we're going to pick one of these, like say this one, and get rid of that lone pair and put it down here so that now sulfur has 2, 4, 6, 8 electrons around it. And so that looks a lot more reasonable. And that one seems to match with A. It also, oh no, it doesn't match with C. So you notice that C has 2 double bonds there. So it's not that it's actually a completely unreasonable structure. We'll come back to that one in a minute. Actually, we'll put a question mark. And then this one down here, we know that sulfur does not have a lone pair. And boy, they have a really odd way of representing that there. So it comes down to A and C. And of the two of them, I think we're going to go with A. There's this thing called formal charge that might be able to get you to consider whether or not these two are realistic, because you remember sulfur can have more than 8 electrons, but AP says they don't do formal charge anymore. So A should be the answer.